To understand how a complex molecule behaves, you first have to find out how its inner framework is actually connected. This framework is built from carbon atoms. They link together to form the physical backbone of almost everything, from the pills in a medicine bottle to the cells in your own body. But here is the problem. Those carbon atoms are usually impossible to see. If you try to scan them with standard equipment, they don't show up at all. To detect an atom using magnets, that atom needs to have a magnetic personality. It has to act like a tiny compass needle that can react to a magnetic field. Without that magnetic quality, the carbon atoms stay silent. They leave us with no way to map out where they are or how they're holding the molecule together. It turns out that 99 out of every 100 carbon atoms in our world are magnetically dead. They have no spin, which means they can't react to magnets at all. You can think of these common carbon atoms as broken bells in an orchestra. No matter how hard you hit them with energy, they will never vibrate and they won't make a sound. Since nearly all the carbon in a molecule is silent, we have to find a different way to listen to what's happening inside. Our chance to see the molecule comes from one specific, rare kind of carbon that makes up just 1% of the atoms in the universe. Unlike the others, this version of carbon is naturally magnetic. It's a tiny functional compass needle. In our molecular orchestra of broken bells, this rare carbon is the only one that actually rings when you strike it. Because we're only listening to 1% of the atoms, the signal we get back is very quiet and difficult to hear over the background noise. Mapping the entire molecule depends on our ability to find and listen to these rare ringing atoms. Older machines used to search for these rare atoms by slowly scanning through different radio frequencies one by one, but it was slow and the tiny signals were easy to miss. Today, we use a much faster approach. We hit the entire molecule with a single massive pulse of radio waves all at once. It's like using a giant mallet to strike every working bell in the room at the exact same time. All the rare carbon atoms vibrate together, creating a messy, overlapping echo of radio waves that fades away over a few seconds. This fading pattern is the raw information the machine records. It's loud at first, then disappears as the atoms settle back down. By hitting everything at once, we capture all the information in seconds. The only problem is that the information is now tangled together in one big, noisy hum. To a person, that raw echo doesn't look like much. It's just a chaotic jumble of waves that all look the same. But computers use a math process to untangle that hum, pulling the messy chord apart into individual notes. Each note is then plotted on a graph as its own peak, giving us a series of clean, sharp lines. This math is the final step that turns a physical vibration into a clear map we can actually use. Electrons surrounding each atom act as a protective shield. Because every spot has a different number of neighbors, these shields vary in thickness. This alters how much magnetic force reaches the center, changing the pitch of the carbon's echo. These different pitches show up as unique peaks on our graph. They tell us exactly what kind of environment each carbon atom is sitting in. By looking at those peaks, a scientist pieces together where every atom is located, revealing the full shape of the molecule. It shows us that even when the vast majority of a system is silent, we can still find the answers we need by knowing how to listen to the few parts